without further ado, I'm Krista. It's so nice to see you all. Thank you for hosting me up in Boulder. As Dr. Stavros mentioned, I'm down in Colorado Springs now. I'll probably be there for a couple years. But I am a San Diego State University, University of California, Santa Barbara joint doctoral program, nice long title there, student. And I'm finishing up that program remotely. So I really appreciate the opportunity to come talk with you all today. Thank you for being here. I'll be focusing on kind of the first component of my dissertation, which is all about spectral unmixing techniques examined for analysis of herbaceous fractional cover and wildfire-prone shrublands in Southern California. So just like my student title, going for a record in length, I am also shooting for a record in terms of long titles here. Okay, great. So who am I? I'm not really sure that what I'm going to share with you today necessarily qualifies as being part of the big data realm, but I feel like it kind of squeaks in just a little bit because I am doing a lot of remote sensing. I don't consider myself to be an expert, but through resources like ResearchGate and Twitter and LinkedIn, I feel like I'm getting connected with the people who are really smart in this field, and I'm learning a lot from them. And I'm enjoying being a student again after a brief time out of academia. And so a little bit about me, I've been doing remote sensing for about 15 years. I got my undergrad from UC Santa Barbara in geography, a minor in geological sciences. And since then I've worked for and with the US Navy, the US Air Force, as well as in the industry. And my interest in wildfires really started about 6 years ago now when I was working for a Castle Rock-based company called Intera. They've created a geospatial software solutions. People are nodding like maybe you've heard of it, I don't know. Or just nodding because you're polite and I appreciate it. But I started working with Intera, and so I was a remote sensing scientist for them as well as an account manager. So I was working with 14 different fire departments across the country, teaching them how to use geospatial software. And they're already pretty well versed in GIS, but they're not used to using imagery from above as much, or they weren't at that time because, right, most people can't fly drones over wildfires. They think you know this unless you have that special permission through the department. And so they weren't incorporating it a lot. But while I worked with them doing that, I was finding a lot of knowledge gaps in the fact that they weren't using these data, they didn't know these data were available, but then at the same time, I thought remote sensing was the answer for everybody's problem, no matter what it was. And I was starting to learn that for wildland firefighters who were working on active incidents, it wasn't always the solution to their problem, because even though we have satellite systems that are going over daily is too late if an active fire front is moving very quickly in 15 minutes. So they really need that real-time data. So I've gotten really interested in looking at landscapes before a fire, trying to see if there's going to be some sort of fuel issue in terms of dry or senesced or invasive species that are really going to spread in case there's an ignition during the fire and then post-fire. And you can see that I've been an enthusiast of fire science and fire technology for a while. That's me at my local fire department growing up as a Girl Scout. So I've been interested in it for a while, but only like seriously working on it for the past 6 years. And so I want to make sure that I mention that a lot of the research I talk about today and a lot of what I've been doing is because I was fortunate to work with an organization called Climate Science Alliance and the Connecting Wildlands and Communities project team. And that's a project team that's been funded by the California Strategic Growth Council through the California Climate Investments Initiative. And it's a collaborative effort with San Diego State University and the Institute for Ecological Monitoring and Management and the Climate Science Alliance. And so it's a team of geographers, ecologists, biologists, hydrologists, city planners, and science educators. And the focus is on shrubland ecoregions, kind of spanning from Santa Barbara down to San Diego, and exploring how connected landscapes can support adaptation and resilience to climate change for both ecosystems and local communities. So rather than a formal research presentation, I already mentioned I'm pretty informal, I'd like to imagine we're going on a hike instead in Southern California. So at the trailhead, I will introduce those CWC-inspired research questions and share some background about why I think this problem is important. Then I will discuss the methods I've used. Then I will show some preliminary results. And then as we reach the summit, which are a lot lower in elevation than they are here in Colorado, I'll summarize what I've learned so far. So changing landscapes, more extreme climate, and growing human populations in wildland and wildland-urban interface areas are affecting the fire regimes in Southern California. The landscape is becoming more susceptible to wildfire ignition and spread as those non-native or invasive herbaceous vegetation growth forms expand and then type convert the native shrublands. And herbaceous vegetation, I might also refer to it as herbs, but basically I'm talking about grasses and forbs. And I've identified critical knowledge gaps that need to be filled in order to help first responders, policymakers, and wildland community members so that they can better prepare for wildfires. Because I think it's imperative that this research be performed to detect and track the expansion of flammable herbs to determine the effect of its presence on the fire regime. So my problem is focused on finding solutions for real life problems. So as we see those native shrublands being invaded and in some cases replaced by herbaceous vegetation, we're finding that the invaders are these Mediterranean annual grasses that have been more prevalent ever since European settlement. And so that's causing an increase in fire frequency, a reduction in fire intensity, and changes in fire seasonality that are all contributing to the elimination of healthy shrubs. And that provides herbs with the opportunity to invade again, and then we get into this grass fire cycle. And so wildfires can be driven by any of the very simplified fire behavior triangle, weather, topography, or fuels. But my focus is on the fuels side. And so I'm trying again, like I did with Intera, I'm arguing that remote sensing technologies can in fact help this problem. So by mapping and monitoring herbs, I'm hoping that we can better understand the consequences of herb invasion and how it affects the fire regime. So I know that in the Earth Lab, there are a lot of people that are focused on wildfire-related projects. In this room, how many people feel comfortable talking about wildfires? Like, should I go over some key terms and definition? Comfortable. All right, well, we'll go really quickly. For those of you that didn't raise your hands, you'll see it flashed on the screen. So wildland fire, we probably feel good with that definition at least. The wildland-urban interface, anything that's adjacent to the wildland area. So we've got the intermix and the interface areas. Ooh, it's quite blurry when it's big. That's good to know in the future for presentations. So my research is not focusing on the rural or the urban, but specifically those more wildland spaces where we're still worried about community members that are tucked into those trees. Maybe they have wood shake rooftops. Maybe they have branches overhanging those eaves. Vegetation and fractional cover, that's going to be a big part of it. So I will talk through this slide. When I'm talking about vegetation cover, I think the simplest way to think about it is just what vegetation growth forms or species are on the ground. So for me in Southern California, I'm focusing on herbaceous vegetation, grasses, forbs, but also chaparral, sage scrub, so true shrubs and subshrubs. And then are they dense, like they are in the spring when there's been some rain, some water that's going to help green it up, help make it more dense, or is it really sparse like it is in the fall or the winter? And then on the fractional cover, that's the mapping side. That's what I'm really diving into with components 1 and 2 of my dissertation. And it's just, if I'm looking at a minimum mapping unit, a pixel on the ground, is it 50% grass, 100% grass? What is that percentage, that cover there? Grass fire cycle, we kind of talked about it. I think you know what that is. And the fire regime as well. And so I did mention that term earlier, just in case. When I talk about fire regime, it's describing patterns of fire occurrences frequency, size, severity, sometimes vegetation and fire effects as well. And so back to the problem. I've highlighted this one part because once again, I want to really hit home that I'm hoping that remote sensing can help with this. So we've got a lot of wildfire experts in here. I should be coming to you. What about remote sensing experts? Who's heard of the phrase remote sensing? All right, good. Okay, who's taken a class? Maybe it was a lesson in your class. Who's taught a class? Oh no. All right, I'm glad I'm asking. Wait, who's never heard of remote sensing and is like, please go through all those intro slides? Oh my gosh, you, great. Okay, well, we're gonna go through it just in case as a refresher for everybody. Thank you for being brave and for raising your hand. And maybe people online too are a little unsure about some of the terms. So remote sensing is the art and science of obtaining information of an object without being in physical contact with it. So I could be centimeters away, I could be kilometers away, as long as I'm not touching it. Sensor 2 touching that object, we're going to call it remote sensing. So it could be weather, it could be x-rays, it could be looking at things on other planets. And so for most of the work that I've done in my career, I've been using satellites in space, so a little bit higher, a little bit bigger pixels. And those satellites are equipped with sensors that, depending on how they're built, depending on their mission, they might have different, what we call bands or pieces of the electromagnetic spectrum so that they can sense different things on the ground. So they can see maybe what we can see with our own eyes, but maybe beyond that as well. And so focusing on spectral resolution, the sensors that I use see beyond what we can see with our own eyes and detect different types of light and energy within the electromagnetic spectrum. So the sun produces a continuous spectrum of energy all the way from gamma rays to very large radio waves. And we see visible light, red, green, blue, but the sun sends us all of these other wavelengths that we cannot see with our eyes. So they hit the ground, some are absorbed, some are transmitted, others are reflected. And everything on the ground has its own unique spectral signature. And so from the data that we acquire from these sensors, we wouldn't even have to see an image. We could actually likely differentiate what it is that's on the surface based on those spectra alone, based on the spectral resolution. There's also active remote sensing. So LiDAR, synthetic aperture radar, or radar, they're sending out their own pulses of energy and they're collecting it again as they go back over. We're not talking about that today, but it is really cool and really interesting. So you all know that. So here's the electromagnetic spectrum. Our eyes are just seeing that visible light, so that very teeny tiny part of the spectrum of this entire option. So there are sensors that are built to capture all that data, and depending on your research objective, you might be working in that. But my focus is really on the visible and the infrared, the near infrared and the shortwave infrared part of the spectrum. And so in order to create data that output answers about my research questions, I can pick and choose pieces of that electromagnetic spectrum, so bands. I can manipulate those bands. And I know that maybe if you haven't taken a remote sensing class before, this could be confusing. So I just like to describe it as thinking about a piano keyboard. So if we play keys on a piano, we hear a sound. But if we choose bands from a sensor, we see an image. So again, if it's a visible image, something we might expect to see with our own eyes, we choose red, green, and blue. And here's an example of what red, green, and blue might look like if you're flying overhead. So these are images captured December 8, 2017 over the Thomas Fire. This was literally the large fire incident that occurred in Southern California. So flying overhead, red, green, and blue, you see the blue ocean, you see the brown and kind of greenish mountains. But since my problem is focused on highlighting vegetation, do you think this is useful? Do you think we can do better? Yeah, we can do better. And so selection of different bands are going to really highlight the vegetation now. So now I've incorporated the near infrared band, and vegetation is very highly reflected in the near infrared. So now you can really see, oh gosh, there's a lot of agricultural areas down here with highly irrigated bright red vegetation. We can also see that the burn scar is a little bit better highlighted and darker brown. So I'm a big fan of this particular combination. And then just while we're here, because it looks cool talking about wildfires, this is what happens if we incorporate some of the shortwave infrared bands. And so now we can see that the healthy vegetation looks blue, the burn scars this kind of golden color. And if your focus area is on highlighting active fire incidents, this is a useful band combination for really honing in and finding those active fire fronts, as well as seeing through smoke a little bit better. And that just has to do with the band selection that we've done. And then because we're in Colorado, here's some footage captured by the Colorado Division of Fire Prevention and Controls. They're multi-mission aircraft. So this is one of those aircraft that are obviously authorized to fly over wildland fires. And so we're switching here between true color and infrared. This is infrared, that was infrared when it's black and white. And so those white pixels are highlighting spots that are very warm. Those are the parts that the firefighters want to focus on. The darker it is, the cooler it is. So that last static image, the one with the blue vegetation, this one, it doesn't have as much to do with my research, but it's awesome. And I like to share it because I think it does a great job of communicating how we're starting to incorporate more remote sensing, how it's useful for more fire-related problems before, during, and after. Okay, so now we'll get to some research. Thank you for letting me share my fun slides. Sometimes I present to much younger crowds, and I find that those are crowd pleasers, so I just like to share them. But again, the objective of my first dissertation component is to determine how well moderate spatial resolution multispectral satellite remote sensing data can be used to accurately extract information from, classify, and estimate that fractional or percent cover of herbaceous vegetation, again with the goal of identifying areas at risk of fuel-driven wildfires. And so for this part, I have evaluated 3 different remote sensing techniques: spectral mixture analysis, or SMA, multiple end-member spectral mixture analysis, or MESMA, and temporal mixture models, or TMM. And with all 3 of these, I tested different types of inputs, spectral bands and spectral indices, and worked with that image data that I acquired on one date versus multiple dates. My goal is really just, where are the herbs? Can I locate them? Can I quantify them? And which technique is going to be most useful to find them? The focus area for my project is San Diego County coastal shrubland ecoregion. So it's the majority of the county, but if you move further east, you get into closer to Imperial County, a little bit more desert on the other side. So I'm really focusing on places that are a lot shrubbier, more chaparral, more coastal sage shrub. And where I've performed the majority of my research is Mission Trails Regional Park, which is outlined here in kind of that orangish gold color. And the reason I selected Mission Trails Regional Park, or MTRP, as my focus sort of sub-AOI area of interest is because it has 5 habitats. It has chaparral, coastal sage scrub, oak woodland, riparian, and a really large grassland area. It's a good example of what we see throughout that entire San Diego County study area. And also, it's no stranger to wildfire. So I've just overlaid a few of the wildfire perimeters and polygons that we've had, just to kind of give you an idea the scale in relation to the study site. It's all burned at one time or another, which is interesting spectrally, because then we can look at recovery rates as well and kind of compare those. So the images on this slide communicate the seasonal vegetation change, or the phenological change from space. And then I've got the 2 field level photographs for March and September from 2020. And the table has precipitation values from that 2020 water year. And it was actually a pretty good year in terms of rain for the county. And those precipitation levels, if we compare those to the imagery, it kind of helps us see why some look so much greener, January, March, April, compared to June, and then even going through September. So the main reason that I'm exploring single date and multi-date imagery is just because of those phenological changes. In the spring, everything is green. The herbs are green, the shrubs are green, the trees are green. But then in the fall and the winter time frame, the herbs are brown, but so is the soil. And so there's always some sort of confusing spectral factor, and that's what I'm trying to pick apart. Here are some field level photographs just to sort of hammer home those phenological changes. And then again, I have the water year 2021 values on the bottom. So significantly less water in 2021 compared to 2020, but we can just see the differences in terms of the green up and then the dry down. And then this is just a 1 by 1 meter quadrat per scale, but it's kind of the same area the whole time. So you're seeing a lot of those changes. And so the data that I'm using are NASA's Landsat data. You say, well, why wouldn't you use something with finer spatial resolution? Because with this, I can go back to the mid-1980s and have surface reflectance data that's already pre-processed for me. And so that's going to be component 2. So component 1, figuring out the methods that work well for 1 year, 2020. Component 2, going all the way back to 1984, so I can look at those changes through time. But that's why I'm not using something like Sentinel that has 10 or 20 meters or something even finer. So I want to be able to go back in time. And then for my reference data, I'm using NAPE data, 0.6 meter pixels. I'm also using near map data, and I can get up to 10 centimeter pixels. And in some of my areas, they've collected 3 or 4 times per year. So I can better differentiate those phenological changes as I'm generating my reference data. And I'm using ArcGIS Pro and Envy and IDL and Viper tools. So the first thing I did was I collected all data, Landsat data from 2020 with cloud cover less than 10%. So I ended up with 8 dates. I spatially subset it, and then I created my index outputs. And I'm looking at normalized difference, vegetation index, NDVI, and normalized difference infrared index, NDII. I masked the land cover that I didn't want to include. So anything water, all urban areas, all irrigated croplands. I'm really just trying to focus on the wildland and the WUI spaces. And then I also used CAL FIRE data to mask out any burn areas from the past 5 years, because spectrally that's really going to have an effect on the data that I'm trying to find, and I don't want to find those just yet. And this is kind of how they show up spectrally. So I created land cover classes of interest, separating herbaceous, true shrub, subshrub, and bare ground. And this side is showing you spring versus fall, and kind of where those show up when you compare the red versus the near infrared. And what I'm really looking for on this is spectral separability. So these loosely drawn ovals, I want them to be further apart, which means that I can differentiate the brown one, the bare ground, from the red one, the herbaceous. And so that part's encouraging, right? I mean, spectral separability, we can see with our eyes that things look different, but we want it to show up that way in the data too. And then this is where I perform my fieldwork, again, in Mission Trails Regional Park. Because sometimes, as I'm sure you all know, things look very different from above than they do on the ground. So if you haven't done field work, I imagine you all have. You look like seasoned veterans. But this is so valuable. And I am such a fan of field work, and I always want people to go out and actually do it and see what they're working on. I mean, because it's remote sensing, right? You think, oh, we can do it from anywhere. Well, things look different. So, so just take a trip, go to San Diego and look around. And then I mentioned that I generated my reference and validation data. So what I did is I took my 30-meter Landsat pixels and I looked at 30-meter pixels, but then I also aggregated them to 90-meter pixels, because when I'm comparing those to the NAPE and the NEAR map, you never know if maybe there's a little bit of a map overlay issue. I wanted to make sure that the percentage, the fractional cover values I was doing would line up all right. Spoiler alert, since I've done this and gotten these results, I'm going back in and I'm using a dot grid method to compare how the dot grid method compares to this more, what my advisor calls sort of like Gestalt method. It's very visual. So I'll have a lot of options for rigorous reference data. And then I went in, I've got all this data that I've pre-processed. I've put it together, I've created my spectral indices, my spectral band combinations. Now it's all about the unmixing techniques. It's the very sexy part of the process, as I'm sure you can imagine. And so SMA, spectral mixture analysis, assumes a mixed spectrum is a linear combination of N members. So N members meaning the very purest spectra I could identify when creating my inputs. So I'm looking for closest to 100% herbaceous, 100% bare ground, 100%, and that's what I'm calling my N member. And SMA assumes that there is a single set of N members for every pixel. MESMA, which is what I run using Fiber Tools, which is a free add-on to NV and IDL, it's a modified SMA. And so it allows for me to take that single set of N members and make it multiple N members so that they can vary on a per pixel basis. So it kind of helps take in that variability sometimes that you might find with topography, shadows, seasonality. So it's just another nice option for comparison. And then temporal mixture models represent each pixel time series as a linear combination of constituent and member temporal processes. So what's different about TMM is that basically on the x-axis is time. So that's where I'm looking at all my different dates, and I'm capturing that seasonality. I can use the NDVI or the NDII. So it's just another nice option.
So in that case,
yeah.
Why it is a single index? It's not the full actual spectrum. It's like some band map combination.
Yeah. And so I can talk about that a little bit more. I have some more slides that show that, but there's different ways to do it. So I will do the index combination, so the NDVI and the NDII, and I've got time. And another way that it's done, and the way that I first did it, you perform a principal components analysis, a PCA first, and then you end up with kind of what looks like that tasseled cap. And at each of those corners, you can separate dark, substrate, and vegetation. And so I went in and I selected all the vegetations, and then that's another way to create a time series. So I can do the vegetation selection from the corners, or I can do the index. Does that answer your question?
Yeah.
Okay. And so here are preliminary results, again, from my more Gestalt method. So I'm rerunning these again as I go with my dot grid method, but they're encouraging. We're finding that separability. So I compared all of my unmixing outputs to those 73 reference data points. And I plotted reference fractional cover values against herbaceous vegetation for each of the 7 dates that I ran. So these are the individual dates of just blue, green, red, near infrared, shortwave. And for SMA, the best performer, according to the slope on the scatter plot, and then the mean absolute error, the MAE, and the root mean square error, RMSE, was a fall date. So 17 November. That's the one that simple SMA deemed to be worthy of further use and further exploration for separation of herbaceous from everything else on the ground. For mesma, again, those same validation steps I was looking at, MAE, RMSE for all of the various dates. The best performer was June. So again, another really dry date. So we're kind of sensing there's a bit of a theme here. The ability to separate herbaceous and shrubs is working pretty well when the herbs are not green anymore. And then I thought with temporal mixture model, those were my most encouraging results for that. So again, the input is a stack of single date bands as opposed to several spectral bands from a single date like I did for SMA and mesma. And so 3 tests per run. So the vegetation, and that's when I was talking about, you've got that sort of tassel cap shape and you pull out the vegetation. I did those for all the dates. And then the NDVI and the NDII. And NDVI was the best performer and also the best out of all the tests that were run. So when I put them all together, in terms of low MAE and RMSE, that was the most encouraging. And so at a high level, I found that unmixing approaches do work well to locate and quantify herbaceous vegetation. If a technique using a single date, if that's the only data set that you have available, ask for something from summer or fall, because that's really what's speaking to the spectral separability of the different vegetation types. But of all the tests so far, the NDVI has been the best performer when run through the TMM, the temporal mixture model processes. And so, as I mentioned earlier, my immediate next steps include validating results for other areas throughout San Diego County. I'm going back with that dot grid methodology. I have 160 plots scattered throughout the county, and within each plot, which is 90 by 90 meters, I have 100 points. And so I'm checking each one of those points and doing my best to make sure that it's really solid reference data that I can use to validate those unmixing outputs. Then I will apply whichever unmixing techniques that performs best to the Landsat data from 2020 to Landsat data from 1984 to present. And the goal with that is tracking herbaceous cover change over time, right? We say herbaceous cover is expanding. Well, where is it expanding? Where do we see evidence of type conversion and replacement? I'm then going to combine those results with fire frequency, fire return interval, and historical fire ignition data, and really dive into attempting to learn more about how the fire regime in Southern California is changing. And so my focus will be on increased susceptibility in terms of ignition potential and the likelihood of uncontrolled wildfire spread, which we have seen definitely in the last 20 years. So I don't think I have to tell you this, but it seems obvious that as temperatures rise with climate change, there will be more fires that burn larger areas of land. But it's been found that predicting future fire regimes is not rocket science. It's far more complicated than that. And this quote really speaks to me. It's something from John Keeley and Dr. Alex Seifert. And I just wanted to share it that this is a tough problem. I'm so glad that folks like you at CU Boulder are working on that. You're solving these issues. You're making the world safer for wildland-urban interface residents, for emergency responders, and hopefully policymakers are listening to you because you're the smart ones that are, making these discoveries and trying to make the world a little bit better and a little bit safer. So I can end it here. I can show slides of temporal mixture model. Happy to go any direction that you would like. So thank you.
I'm really interested. So this kind of overlaps with a project that we do have going, where we're kind of looking at compound disturbances and changes in sort of regeneration. So rather than, let's say, how the vegetation changes the fire regime, but how do different disturbances affect the way that systems recover and regenerate.
Right.
And so, but we're kind of using a lot of different sensors, everything from like a 4-band sensor on drone through imaging spectroscopy with 430 bands from the neon AOP. And so I guess I'm just wondering with, because the TMM seems really promising, but it distills all that information down into like a single index.
Right.
Or your single sort of tassel cap. So I'm just wondering if you have any thoughts about leveraging a more complete spectrum than you would get with a single band or a single index.
Yeah, right. More data, more information, but more time. Right?
It's more complex.
Yeah.
There's more dimensions. So
Right.
I guess I was wondering if you've seen anything about how anybody might have. I mean, it's hard because imaging spectroscopy data hasn't been available in time series. And
Right.
it's only just starting to become available with the like shift campaign. And
Right.
But you might have Hyperion. I mean, it's decommissioned, but that's if you.
yeah, I mean, Hyperion's the problem with it is that it had a really low signal to noise ratio, and so a lot of people stopped using it, unfortunately. But I was just wondering if you had any thoughts or came across anything of using time series with the higher dimension data.
All I've really seen with time series so far is the Sentinel Landsat use data. So I've not seen anything with really, high spectral information. I think that would be fantastic. No, that would be amazing. And I feel like so yes, for this part, the TMM is what worked really well, and DBI worked really well. As I keep working to validate my data, I'm finding the simple SMA is also working quite well. And with the simple spectrum mixture analysis, I'm using the tool that's built in the ENVI, so the linear spectral unmixing tool. And it's not great with Landsat data because the spectral resolution is just a little too coarse, but I could imagine something with hundreds of bands that's right up the alley of it. So I think maybe that might be a good way to go. I just don't know. Stay tuned, right? We always think we're going to be done. Like when Natasha and I started talking, it was like, oh yeah, I'll be done with that next part in a few months, no problem. And then it's here today, and I'm like, oh. I'll have a better answer for you.
I think Jennifer's got it.
Okay.
Yeah, that's just the way we roll, right?
Thank you for understanding.
I just wanted to say thank you for your great talk and appreciate the accolades of what our group is doing, but also just wanted to say you are smart and making great contributions to the important questions and decision-making contexts, which is partly my question, which is, given your wealth of experience working with stakeholders and different groups, like what are the decisions that are driving your study here in terms of like, okay, great, once you do get those annually resolved spectral mixed maps of herbaceous and shrubland, what's the decision that you can support, or what's the knowledge that you're hoping will make a difference in that context?
I'm so glad you asked the question. So my hope, especially after, I don't know if people need to see me on camera. I'm back. My hope is that I will output maps with these, and those can be incorporated in something like Landfire or Intera software, something that's freely available to everybody. Because something that Intera was working on before I was leaving was really ramping up their inspections program, but that meant boots on the ground. It meant their fire marshal and their team of 5 people for all of San Diego City were visiting houses in areas where they assumed were at high risk because they were on canyon lands. But that takes a lot of time. They lost a lot of funding. And so I'm hoping that these type of maps can be incorporated and shared with first responders so that they see, oh gosh, right here we've got a really high fraction of herbaceous vegetation. Let's target that first. Let's make sure the mitigation steps are performed there. Let's make sure that's where the fire marshals are visiting and passing out flyers and educating the community members during town hall meetings to ensure that they're aware that they have a really high fire risk. So, you know, if I can fill a gap in the research world and help with that, I mean, that's absolutely a goal. But I'm really hoping that people will take this and it'll just inspire them to make more maps that can be used by first responders to educate the community members.
And do you know, so I've got a couple of other questions too, actually. So I'm not familiar with Near Map. I'm sure what the heck is that?
It's beautiful, right?
That sounds amazing.
It is amazing. So Nearmap was a company that originally began in Australia, but it's satellite sensors that they fly 3 to 4 times a year. San Diego State has an agreement with data, so it's not free data. You do have to engage in.
Where do they fly, or what do they cover? Is it California based, or is it
the entire country, but not 100% of the country. So they want to get to the full country. But right now it's mostly focused on sort of urban and then just that wildland urban interface area. So like state parks, national parks, those bigger wildland spaces. But I talked with some of the folks that started the company and they said, yeah, we focused on urban areas first, but now they're finding that a lot of folks like us are reaching out and we're saying, hey, we'd really like to be able to monitor this wildland space and learn more about that. And so they don't have a per image cost. You can't just buy images, they have subscriptions, but they do have different subscription options. Sorry, I've done a lot of research on this recently, so you're like, oh, it doesn't matter, we don't need to learn about this.
maybe we can follow up.
It's really cool.
Training.
Yeah. And so
ears, I'm sure, perked up with this.
Yeah. It's amazing when you zoom in. Like when I go to Mission Trails Regional Park and you see the hikers and you see the brand of backpack they're wearing. You know, it's pretty amazing for something that's, you know, available to at a civilian level. You don't need a secret clearance. Right? Right. But it is just RGB. Like it would be fabulous if it would get into the infrared range, but
you still do a lot with that though.
Yeah.
Okay, so one more question. Oh, sorry.
How far back does that go?
it goes back to 2014. Well, it depends on your location, but 2014 is kind of when they started in the US. So yeah.
I appreciate learning about that. I have one other question for you, which was, you made a statement in your intro about the expansion of herbaceous cover.
Mm-hmm.
Where's that coming from? Has anybody done that study west-wide, like expansion of herbaceous cover and that? I mean, you've done work showing the distribution of cheatgrass specifically. Anyway, just curious where that's coming from.
Yeah.
And if you can point me to who's doing that work.
Yeah, no, absolutely. So one of my committee members, Dr. Alexandra Seifert, she was, on the quote about fire regime. She's kind of my first go-to, my first point of contact when it comes to that. And so a lot of her studies have been San Diego County, Santa Monica Mountains. And so pretty much anything that Alex has done, I start there and then I kind of branch out from there. A lot of what I'm reading is definitely about cheatgrass. A lot of places in the basin for sure. And so we're seeing it in Southern California too. I don't know how it compares to basin range, but
yeah, no, it's a great question. I guess I'm pointing to it because I think it's a really important question to answer. So as you make progress on the spectral unmixing, and we've got a project working on spectral unmixing, we're focused on forested systems. Mm-hmm. That's what's driving our questions, but we're going to get to some of the other veg types too.
Yeah.
But so anyways, there's like important questions to be answered there. I guess is kind of where I was circling around.
Yeah.
Just food for future thought.
Absolutely. Well, I love that you're starting from like the forested and you're going, I'm starting from the grasses and I want to go to the forest. So let's meet in the middle. Yeah.
So the CU is a great place for this talk because Envy was developed here as well as some of the techniques in spectral unmixing. So yay for that. So I'm just curious about your next steps. So using Landsat series.
Mhm.
So yeah, you mentioned that summer and fall are where you're really being able to distinguish these cover types that you're interested in.
Yeah.
And I'm wondering if you considered using like the CCDC algorithm or other algorithms that kind of let you leverage the complete Landsat series.
Yeah.
And you look at patterns of greening and browning to try maybe as a way to help distinguish your the herbaceous from the natural vegetation or the chaparral.
Yeah, I had not, but CCDC, I'm gonna do what do
Yeah.
you know? No, that's fantastic. Yeah. So that you think that
One of the advantages to CCDC is that it does take into account the phenological cycle and
Yeah.
is looking for like drastic shifts.
okay.
That's how it's usually used, but it you may not have the drastic shifts. You may have sort of a trend within the cycle, and you can use CCDC to pick that up too. So I think it would be appropriate, even if you don't have kind of drastic changes in your system. I think it might be a good
Have to use the trend for fractional cover? Or?
Well, you could, and that's actually what I was thinking. I haven't seen, you could potentially calculate the fractional cover going all the way back, and maybe even sort of include that as bands and the input along with the regular spectral bands.
Yeah.
So there might be something interesting there
Yeah.
to play around with. I'm not sure.
No, absolutely. Well, and so between 1984 and 2020, I'm starting by choosing the years that have similar annual precipitation values so that there's not too many extremes. So I'm really intrigued when you're saying looking for trends in something that, aside from just the extremes too. Okay. I like it. Thank you. I'll add you to my acknowledgement section when it works and blows all the other unmixing techniques out of the water. Natasha, did you have another question?
I think I was going to ask, so, you know, if your end goal is sort of like decision makers and you're using NV, and NV's proprietary is pretty expensive.
Right. Thank goodness for student licenses, but yes, it is quite pricey.
Yeah, I mean, I love NV for what it is.
Mhm.
It can be quite powerful, but it is pretty exclusive in its use. And one of the things we're interested in at Earth Lab is sort of more open science, and you know, it's great that you're producing maps. But if, let's say, Intera, who serves the nation, wanted to expand this, are you using any open source languages or like any of the platforms like Google Earth Engine, or have you looked into those? And if so, is there a reason why you shifted away from them and toward them being instead?
That's another really great question. So I should mention, I think it was on my bio slide. So I wear a few different hats. I'm also a remote sensing scientist for a small Virginia-based company called Solus Applied Science. And with them, I'm really pursuing different options. I'm getting more into coding, which is something that's always intimidated me, but I'm really excited about it. Now I'm just dangerous enough to make things happen. And so back on the student side, I do use Google Earth Engine. I love it. And I've been learning how to do so many different things. I love the speed. I love all the access to the data, all the reasons that we enjoy it, right? But what I wasn't totally confident doing in GEE was the spectral unmixing. And so that's why I just kind of went back to my comfort zone of NV, because I knew if I was using those 30 meter pixels, I was going to need to do that unmixing so that I could get in there. I've seen on the developer sites that some people are doing spectral unmixing in GEE, but I'm just not at that level of expertise just yet. But that's something that it's kind of like, you know, when I'm sitting watching the Broncos play on Sunday, like I've got GE on my lap.
I just checked. It is implemented now in GE.
Is it?
Image.unmix.
Yeah.
I don't know. I don't know if all of your methods are implemented.
Well, that's amazing.
Just
technology,
like
right?
It's once they implement those algorithms, they're sort of black box. And
Yeah.
so there's a lack of flexibility,
Yeah.
generally speaking, but it can be a way to test some things without
Yeah.
having to download data
Yes.
on larger geographic areas. But
Yes.
once you need to do specifics, it starts to get pretty tricky.
Yeah. Okay.
Yeah, if
possible.
you're like me, my coding in GE is like, find someone who's already done it.
Right.
And
Yeah.
And it's a, yeah.
I mean, so much about
Like,
it
I'm
is-
not really a Java coder.
Yeah.
so much of the benefit of it is just being able to like pull up data quickly and look at it.
Yeah.
And proof of concepts. And like there's some things that you can do that are really rigorous in our engine.
Yeah.
But sometimes you can get into a place where you can't do what you want to do.
And it's, oh, it's killer. It's just, you have to like take a few hours and go for a walk or something and just mope when you can't figure it
Krista,
out.
have you seen our earthdatascience.org website?
I visited it this week, yeah.
Yeah, because they've been, I mean, Nate here is the director of the education program. Elsa, I think, might be online. They've got some great coding tutorials.
That's awesome.
Dabble.
Okay. Well,
We're
nice.
open to feedback too.
Oh, great. Yeah. No, well, so I feel like I'm all over the place with my presentation and just my biography in general, but it was like half of me wanted to return to PhD. I never thought I would pursue a PhD. Like the master's, I was like, oh, okay, that happened. But like the PhD, I was like, no. I want to be a doer. Like I don't feel like I'm a strong researcher. I love pressing buttons and playing with it. But it was those knowledge gaps working with Intera. But then also, I really want to be a professor. And so I'm always looking at, especially like open source opportunities. And I want to write labs in GEE. And so I love the community that they've kind of built and how they're all working together and for the greater good and knowledge.
So I was a TA for the intro to remote sensing class here at CU Boulder for undergrads and graduate students. And
That's
I've come up with, I have a list of about 12 Google Earth Engine labs that I'm trying to share more widely. So
Yeah.
if it's something that you'd be interested in looking at
Very
and
happy to look
providing
at it.
feedback, that'd be awesome. So I'll
Yeah.
follow up with you on
Oh my gosh, please
email.
do.
Yeah.
It's not on there. I'll make sure everyone has my email address and I'll
Yeah.
follow up, especially with a link to Nearmap so that you have that and can look into it. But yeah, I mean, if you all want to keep in touch, I would love it because I think I have so much to learn from. I know I have so much to learn from all of you. When I saw those hands being raised, I was like, all right, let's switch sides. I'll sit down and just take notes from you.
Or vice versa. Yeah, there's lots of folks in this group who work on invasive species and biodynamics and new concepts, open source software. Yeah, there's a lot here, so you should definitely reach out and connect. And come visit us. This seminar series is ongoing, so please join us.
Thank you. I'm on the listserv
Okay,
now, so I can dial in, and I appreciate the opportunity to make it up to Boulder. My spouse and our dog and I made a little day trip out of it, and seeing fall colors. It's fun seasons. We didn't really have those in San Diego, so it's nice to be back in Colorado.
Yeah, thank you.
Thank
It doesn't
you.
look like there are questions.
I didn't see any. Thank you.
Thanks so much.
Thanks everyone online.
Thanks for attending. Should I stop?